Hello, everyone, and welcome back. My name is Mr. Kovalt, and in this video, I'm going to be talking about radiometric dating, and we're going to start off with radiocarbon dating. So let's get into this. So, number one, radiocarbon dating. What is radiocarbon dating? Well, radiocarbon dating is a method of dating objects that have been part of living organisms. So, if they're made up of living organisms or what was once living organisms, then you can use radiocarbon dating to measure the ages of those things. And I'll explain why in a moment. So this is going to be used to measure the ages of things like fossils or some sort of artifacts that were made up of living materials. So, for example, you can measure anything like scrolls. We have the Dead Sea Scrolls have been dated using radiocarbon dating. Dead Sea Scrolls are made out of plant-like material. Any cloth, for example, that is made out of plant-like material. So, for example, the Shroud of Turin has been a focus of radiocarbon dating. For those of you who are familiar with the Shroud of Turin, that is the shroud, the burial shroud that Jesus was supposedly buried in when he was entombed. You can date fossils like trilobite fossils. So if you're digging in your backyard and you find a fossil or what you think is a fossil, you could use radiocarbon dating to date that. So again, this is used on anything that was once living or made up of once living things or materials. And the reason for that is because it is based on carbon 14. So carbon 14 is a particular isotope of carbon that exists naturally in nature. It's a very small amount of it is a very small part of your carbon or amount of your carbon is actually carbon 14. And this is created in the upper atmosphere through neutron bombardment. So what that means is that you have nitrogen. So you have nitrogen 14 in the atmosphere. It's going to be bombarded by a neutron. So that neutron is going to incorporate itself in the nucleus of the neutron. And so that then causes carbon to be formed. Carbon 14 plus hydrogen as well. So this is the process that goes on to create your carbon 14 or the very little of it that you have. So then this is a constant process that's happening in the upper atmosphere. And then there's the decay process. So this is carbon 14 is a radioactive form of carbon. So this is going to undergo decay. In particular, it's going to undergo beta decay. And so carbon 14 is then going to go back to nitrogen 14, and it's going to release a beta particle. The half-life for this process is 5,715 years. So these are two constant processes. So that way, if you know the amount of carbon 14 in the atmosphere like today, and you find an artifact that you want to date that was once made out of living material or is made out of material that was once living, then you can know what the age is by measuring the present carbon 14 in the artifact you found and compare that with the present day carbon 14 in the atmosphere. So you can get a ratio. You can use this by comparing the ratio of carbon 14 to carbon 12 in the atmosphere presently compared to the artifact you found. The ratio of carbon 14 to carbon 12 in the artifact you found. So you can then figure out what the age is. For example, let's say I find an artifact. Let's say I find a manuscript of something. I don't know, some ancient book. Let's say Aristotle's De Anima or something along those lines. Some book by Aristotle or Plato or some ancient Greek, and I want to measure the the age of that manuscript, right? So what I can do is I can measure the carbon 14 to carbon 12 ratio in the manuscript, compare that to the ratio that is presently in atmosphere. And let's say I find that there is 25% of the carbon 14 in the manuscript that I find in the atmosphere. So I have 75% less of the carbon 14 in my manuscript compared to that which is in the atmosphere. And so if that's 25%, and I know the half-life is this, then I know that the definition of a half-life is the amount of time it takes for half of your original amount to decay. Then if I know what the original amount of the carbon 14, assuming that the carbon 14 that is present in the atmosphere today has been present at that same level through time, then I can say, well, the original amount of the carbon 14 is what I have in the atmosphere right now. So that must have been the original amount in the artifact or the living material when it was alive. But when that material dies and it's used to make things, then the carbon 14 is no longer taken in by the animal, right? So humans, animals, plants, they take in forms of carbon 14. Humans, we're breathing in the carbon 14. We're getting it in our food. We eat plants. Plants are taking in the carbon 14 in the form of carbon dioxide, right? So there's a constant replenishing of the carbon 14 from the atmosphere. But when I die, or the animal dies, or the plant is made uh, used to make other things, then it's no longer living and taking in the carbon 14. And so at that point, the carbon 14 is decaying from its present amount in the atmosphere. So that's why I can take this amount in the atmosphere and compare it to what I have in the artifact. And so if I only have 25% of the carbon 14 that I find in the atmosphere, then I could say, okay, well, if the half-life of carbon 14 is 5,715 years, and I know that it takes that amount of time to get rid of half of my original amount, and I've only got 25% left. So in order to get to 25%, I would take a half of 100%, that's 50%, and then take another half of 50%, that would give me 25%. That's two half-lives. So then I could take the two half-lives and multiply 2 by 7,515 years, and I'll get about 11,400 years or something like that. So that would be the date of that particular object that I was dating. Okay, so that's how radiocarbon dating works. However, there is a 5% deviation due to the variance of atmospheric carbon 14 over time. So over time, it's not as consistent or constant as we would like to believe. That variance in the atmospheric carbon 14 leads to a 5% deviation. That would be like if I date something and it says, and I calculate it to be 6,000 years old, then that would be like a 300-year variance, so plus or minus 300 years. So that's kind of a large difference, but we can correct for that difference or that variation or deviation by using tree rings. So we can use tree rings in the western Bristol pine tree. They're very, very old trees, and so what we can do is we can look at the tree rings, because every year the trees make a new tree ring, and in each of those rings, while the tree is living, it's incorporating carbon 14, and so we can use the tree rings and measure the amount of carbon 14 in that particular tree ring to get an accurate picture of what the carbon 14 level was at that particular year. And so we can compare that with what we know with the carbon 14 that we're measuring in different objects. And so we can use that, and we can go back in time comparing the living trees with the dead trees, right? So if there's an overlap between, say, a dead tree and a living tree, we can then use that to extend the amount of time uh, that we can go back and measure the amount of carbon 14 in each of the years, right? So if there's an overlap between a dead tree and then a living tree, we can then chain them together like a chain because they're overlapping, and we can go back further in time to measure the amount of carbon 14 in each of those years, and then we can use that to correct and make carbon 14 dating more accurate compared to the tree rings. Um, so uh, this is only used for things that were once living, as I said. So you can't use this to date rocks. You can't use it to date anything that wasn't living at one point or made up of things that was living at one point. So rocks and things like that are not going to be objects that radiocarbon dating is going to be used for. And this is only accurate up to uh, objects that are less than 50,000 years old. So anything that's older than 50,000 years old is not going to be useful for radiocarbon dating. So then, what do we use for things like rocks or the earth or things like that? Well, we got to use other ways or other radiometric dating techniques, and I'll get to that in just a moment. Okay, so the next kind of dating that I'm going to talk about is called uranium lead dating. This is one of the most dependable techniques for dating things that were never living, like rocks. This, like the carbon 14 radiometric dating, this relies on a ratio of isotopes. In this case, it relies on a ratio of uranium 238 and lead 206 that's within igneous rocks. Now, igneous rocks are the rocks that are formed from heat, like volcanic rock. And so when the igneous rocks form, it's going to have a certain amount of uranium 238 to start with. What I talked about in an earlier video was the decay series of uranium 238, which ends in lead 206. Lead 206 is the final product of the decay series because lead 206 is stable and it's not going to undergo any more radioactive decay. So this process of going from uranium 238 to lead 206 is a very long process. The half-life of this process is 4.5 billion years. So, as I said before, the half-life of something is the amount of time it takes for half of the original sample to decay. So that means that if I have a sample of uranium 238, it's going to take 4.5 billion years of that sample to decay into half of what I have left. So to decay or be half there or half gone, it's going to take 4.5 billion years. So what does that mean? That means that I can use the relative amounts of uranium 238 and lead 206 to determine the age of certain objects that I want to find the age of. So like the carbon 14 dating or the radiocarbon dating technique, where I compared the ratio of the carbon 14 to carbon 12. Here I'm comparing the relative amounts of uranium 238 to lead 206. So how does that work? Well, what I do is I assume that I find a rock, I say igneous rock, and I find some lead in it, right? And I find some uranium in it. So the assumption is always going to be that any lead 206 in the rock used to be uranium 238, since uranium 238 decays into lead 206. So I assume in the rock that I find that it must have started off with 100% uranium 238 and zero amount of lead 206. So with that assumption, I say, okay, I find a rock, and let's say I find that, it has equal amounts of uranium-238 and lead-206. Well, so if they're equal amounts, I assume that, well, okay, so any of the lead-206 that I have, I'll assume that used to be uranium-238. So from there, I can infer that half of my uranium-238 decayed, the original amount decayed. Because if I take half of that, right? So let's say I have a gram of uranium-238, and then I start with, then after one half-life, half of my uranium-238 will be left, and the other half was converted into lead-206, meaning giving me equal amounts of lead-206 and uranium-238. So if I find a rock that has equal amounts of uranium-238 and lead-206, I can assume that the original amount of my uranium-238 decayed by half. And so I would measure or date that rock to be 4.5 billion years old, because the half-life of uranium-238 is 4.5 billion years old. And since I have half of my uranium-238 left from what I assume to be the original amount, then I know it's undergone one half-life. So this assumes, again, that no lead-206 at the time of the igneous rock formation. So at the time that this rock was formed, I assume that there was no lead to start with, because of course, if there was lead 206 to start with, and my assumption is any lead 206 that was there, right, came from the uranium 238, that would be a false assumption if it started with lead 206 to begin with. Well, we can test this assumption, because the lead that results from the decay of uranium in the lead to start with has a different isotopic composition from the lead that may have been deposited there at the time of the formation of the rock. So we can use that to test the assumption. And so with this type of dating, uranium lead dating, we can use that to date the age of the Earth, because we can use that to date rocks all over the Earth. And the rocks in the Earth that we have dated all over the Earth have given dates ranging for about 4.5 or 3 billion years old. So we can use this dating to date the age of the Earth. There's also another dating technique called potassium argon dating that's also been used to date the Earth or date rocks on the Earth. And that also has a very long half-life as well. And that's it for radiometric dating. I hope you found this video interesting and informative. If you did, then by all means, please like the video, smash that like button right down there. And also make sure you subscribe to my channel, hit that notification bell. But when you do, make sure you hit the all button. Click on that all button so you can be notified by all the videos I put out. And finally, put a comment down in the comment section below. Make sure you ask me a question if you've got them, and give me any feedback. Thank you for joining me, and have a great day.